Okay, today we have Isaac Ortigoza coming from Symmetric to tell us about the symmetric topological complexity of the torus. Adelante, Isaac.
Thank you. You can see something? Okay, perfect. Oh. Well, I am Isaac, and I'm going to present today the symmetric and symmetrized topological complexity of the torus. Well, the sectional category of a fibration P from E to B, denoted by the C cat of P, is a least integer n such that the base space can be covered by n+1 open sets, and on each one of these sets, P admits a cross section. Well, the topological complexity, the TC of a space X, is as the sectional category of the evaluation map that takes a free path in X to its endpoints. We can take the restriction of this fibration to the configuration space of 2 points to obtain another fibration. The total space in this fibration is called the non-loop space, and it is the complement of the free loop space in the free path space on X. The group C2 acts on the non-loop space by traveling in the opposite direction. Also, C2 acts in the configuration space by switching coordinates. Then, if we consider the quotient of this fibration, we get another fibration that we are going to talk about in a few minutes. Most of the motivation comes because Farber, Tabachnikov, and Yubersky prove that the immersion problem and the TC problem is the same problem for RPN, except for the cases n equal to 1, 3, and 7. Also, Jesus and Landweber proved the problem of the TC is equal to the embedding problem, except for the cases 6, 7, 11, 12, 14, and 15. Farber and Grant introduced the concept of the symmetric topology, and Basabe, Gonzalez, Rudiak, and Tamaki introduced the concept of symmetrized topological complexity of space X. This is due to the need to create a move planning that satisfies the condition that the way that you go from the point B to the point A is the opposite move to go from the point A to the point B. We get the two definitions. The first definition is the symmetrical topological complexity, and is one more than the C-cat of the evaluation map given in the first in the diagram, the first fibration. Okay, the symmetrized topological complexity is the C2 equivalent sectional category of the fibration that given by the evaluation map. It is the the last vibration. Well, Don, Basabe, Gonzalez, and Rudiak and Tamaki has observed the first inequality. Also, Farber and Grant observed that the TCS is less equal than 2 times the dimension of X, and the work of Cohen and Van Koop implies that the TC is equal to the TC sigma, and it's equal to the TCS of a space X for any closed surface, orientable or not orientable, of genus at least 2. And there's an analogous equality for the spheres, and it is equal to 2. Jesus Gonzalez used the massive work to show that the TC of the TC sigma and the TC S of the projected plane, it's equal to 4. My central result shows that the TCS of the torus is equal to the TC sigma of the torus, and it is equal to 3. Then this finish the this invariant for all closest surface X. This is the result shown. Well, to understand this, to prove this theorem, we have to understand the sectional category in terms of the joint map. Well, if P is a fibration from E to B, the C cat of P is less equal to N if and only if the N+1 joint map of the fibration P has a cross section for all the base space. Well, I was interested in the first and in the last vibrations. The first vibration is that the vibration that give us the TC of SpaceX, and the last vibration, the first one, give us the TCS of the SpaceX. Well, to understand how does the fundamental group of the base act on the fiber, we have to understand first which is the true fiber on this vibration. No? The true fiber is the map of the 0, 1 to X that sends a path to starts in X0 and ends in X1, and the maps from the 0, 1 to X that sends the 0 to X1 and 1 to the X0 module set C2. And if we take a element of the fundamental group, we have to understand this element as the two steering right group over X, such that for each element in this fundamental group, we have two paths that are in X. That for each T, the cardinality of alpha T and beta T, it's equal to 2. Also, its endpoints and the starting points are X0 and X1. Also, we take an arbitrary order to these points, and we choose alpha, the path that ends in X0, and beta, the path that ends in X1. Well, I use the the formulas that Arminio Costa and Michael Farber gave to understand the first vibration, and these formulas explain how does the monodromy are acting on the fiber. Well, I use these formulas and I see that I can project these formulas to the quotient, and I get a square that all the front triangles of the squares commute. Well, in a geometry way, if we have a path from x0 to x1 and a true right in x, the way that will leave this path in the fiber is by the formulas that I get, is traveling first for traveling first with alpha, and then going to omega, and then going in the opposite way of beta if the bride is a pure bride. If the bride is not a pure bride, then the order that we are traveling is first going first traveling around beta, then going around omega, and finally going in the opposite way, in the way that that is alpha, like we can see in the pictures. Well, if F is the homotopy fiber of P, the n+1 joint map has for homotopy fiber the n+1 joint of the fiber F. Also, we can see that the fiber is at least n connected. Then the first obstruction to create a section of the n+1 joint map is a cohomology class in the H n+1 of B with coefficients in Pn of the n+1 joint of the fiber. Well, the twisted coefficients are equivalent to the tensor product of the reduced homology of the fiber. Well, if we use an element of the fundamental group of X, and we interact this element with with a bride, with a true steering bride. Oh, sorry. With a true steering bride. We need to understand this element of the fundamental group as a path from x0 to x1. Then we have to choose a fixed path delta, and we use the formulas that I already explained in this picture. And using these formulas, we can understood how does the action of the fiber acts on the fundamental group of X. Well, This is for a Braid, for a no pure Braid, acting to an element of the fundamental group. Then we have an action of the Braids on X to the interior ring of the fundamental group of X, given by the formulas that are showing. And also the fiber that we already understood, it's equal to the I0, and the I0 is the augmentation ideal of the integer ring. Okay. Also, the Schwarz theorem says that the first obstruction to make a cross section of the to create a cross section of the n+1 joint map is the n+1 product of the first of the first obstruction to create a cross section of the fiber P. Well, to understand how does the Braids work in the torus, we consider a torus with a thin shell, and the outside boundary is going to be T0, and the current boundary is going to be T1. Well, if we make a cut in this torus, thin torus, we can understand a Braid as you can see in the picture, no? To steering that start in the first torus and end in the current torus. If we project to the plane this picture, this tube, to a plane, we get these diagrams, and we can simplify Braid by using Bradman's moves to simplify Braids. Also, to understand how to concatenate two Braids, you have to put one diagram in the blue bar, in the blue bar that is in the pictures. Well, John Bierman give a presentation of the two Braids of the torus, and Marasugi and Kuripita give us a presentation that a presentation of the Braid group that is generated by three elements, where A squared is commute with everything, B squared commute with everything, and also A squared and B squared it's equal to C squared. Also, the Marasugi and Kuripita give us a extension of B2 of T to solve the word problem. I use this extension, and I found a Tuku cycle that classified this station. I call it this Tuku cycle Palin. And with this cycle, I can understand the Braid group as a product of the first group with the last group perturbed by the Tuku cycle. This is that if we have a Braid, we have a canonical expression of the Braid, where is the form of A to the 2n times b to the 2m times omega, where omega is a word in ABC that all its exponents are equal to 1. With this formula, with this expression of the Braids, I use this expression to understand how does the Braids act itself, and I use this formula to create a free resolution over theta over C for the CB2 of T. I construct this free resolution. I construct this free resolution to be able to calculate products in cohomology. With this resolution, I also calculate. I also give a homotopy contraction of this free resolution, and I use this free resolution, this homotopy, and the theorem of Handel. I use the Handel theorem, and I give a diagonal approach to this free resolution. Well, with this resolution and these formulas, I was able to construct. I was able to construct the products in cohomology. I give explicit formulas to calculate the products in cohomology from the BT2 with coefficients, with twisted coefficients in G times the cohomology of BT2 with coefficients in G to the cohomology of BT2 with coefficients in the tensor product of G with G, where G is CB2T model. Well, for the case that I was trying to understand, I have with the monodromy that I already explained how does it works. Oh, sorry. With the monodromy that I already explained how does it works, I was able to found the primary obstruction to create a section, and this primary obstruction is represented by the map that goes from B2 of X to E0, given by the formula that it shows, using the convention that I already mentioned, where gamma is a Braid that given by the two paths alpha and beta, where alpha ends in x0 and beta ends in x1. And this is the one dimension cohomology class, and is the first obstruction to create a cross section in the vibration of the evaluation map, and this cohomology class is a cohomology class in the bar resolution of the zeta with the rings zeta z z b2 of t. Well, my resolution in the first dimension is a subgroup of the first group on, I mean in the first dimension of the bar resolution, and this cochain class that I already mentioned, my obstruction class, is the restriction in my resolution of this map. Well, using my formulas, I was be able to calculate the 3 power of this cochain class, and I obtained the obstruction cochain, and it's given in the generators given by this. And the problem that I was trying to solve is if this cochain is going to be 0 of it's not going to be 0. If it's going to be 0, then I could be able to make a cross section to the 3 joint map of the evaluation map that determines the TCS of the torus, and I could find a map that factorized the map that I found, and this is the map that factorized this triangle. Then this is the this obstruction is equal to 0, and because this obstruction is equal to 0, then the TC of the torus is equal to 3, because this obstruction was the last obstruction. My pre-resolution it ends on dimension 3, and well, this is the last obstruction. Then we have that the TCS of the torus it's equal to 3. Well, with this result, we have that the TC sigma of the torus has to be also 3, because because 3 was less equal than the TC sigma of the torus, and this is less equal than the TCS of the torus. Well, well, this concludes the theorem that I mentioned in the beginning, this theorem. And this is. Sorry, I was a little nervous.
Okay. Thank you very much, Isaac.
Also, I have to say something. This give also an example where the inequality of the TC sigma is strict. Then it is a good result. Mhm. I was running. Well, do you have any question?
Are there any questions?
So I have a question at the very beginning of the talk when you talked about a result of Jesus and Peter about the embedding dimension of real projective space. That it wouldn't be the TC. What?
There is a typo in that formula.
Yeah. Is it the symmetric TC?
Symmetric
yes,
TC?
we forgot to add TS.
TS, sorry. Yes, you mean this
There.
one? Yeah, it's TS. Sorry.
So is that symmetric and symmetrized? Are they necessarily equal for that one? Jesus, do you know?
Well, this is a classical thing. Essentially, the reason that I studied the symmetrized thing for real projective spaces is because it has to do with the existence of non-singular bilinear maps. And
Right.
and the symmetric stuff is just embeddings. So, well, this is a major problem, whether they are the same situation or not. But if a counterexample might exist, well, it's quite possible that it will be in real project spaces.
Okay, thank you.
Any other question?